Hello everyone, myself Dr. Harisankar Singh. So far we have discussed three Maxwell equations. Now in this video I will be giving the details of fourth Maxwell equation, that is Ampere's Maxwell equation. As we have discussed this generalized form of Maxwell equation, so here our concern is focused only on the fourth equation now. Initially, Ampere's law relating a steady electric current to a circulating magnetic field was well known. By the time Maxwell began his work in this field in 1850s, thereafter Maxwell modified the Ampere's law. However, Ampere's law was known to apply only to the static situation involving steady current only. It was Maxwell addition of another source term, that is a changing electric flux, that extended the applicability of the Ampere's law to time dependent condition, and this made the Ampere's Maxwell equation. So in the differential form, Maxwell fourth equation is written as del cross H is equal to J plus del D by del T, where J is the conduction current and del D by del T is the displacement current. Del D by del T is extra term added by Maxwell into the Ampere's law, whereas in the integral form it is written as closed integral H dot dl over contour C is equal to surface integral J plus del D by del T dot ds. The main idea of the Ampere's Maxwell law is an electric current or a changing electric flux through a surface produces a circulating magnetic field around any path that bounds that surface. In other words, a magnetic field is produced along a path if any current is enclosed by the path, or if the electric flux through any surface bounded by the path changes over time. Here is the expanded view of the Ampere's law is given. Closed integral B dot dl over contour C is equal to mu naught in bracket I enclosed plus epsilon naught d by dt surface integral E dot n cap dA. And in this equation, the closed integral tells you to sum of the contribution from each portion of closed path C in the direction given by the right hand rule, where B is the magnetic field in Tesla and it is vector quantity, so arrowhead is there. And the dot product tells you to find the part of magnetic field B parallel to the incremental length dl, and it will be along the path C, and dl is incremental segment of path C. Mu naught is the free space permeability, and IENC is that enclosed current contribution will be taken into the account, and epsilon naught is the electric permittivity of the free space, d by dt represents rate of change with the time, and surface integral E dot n cap dA is basically electric flux through a surface bounded by path C. So in this equation, the first term is the basically conduction current term and the second term is basically displacement current term. We will discuss in more details later on. Thus, the Ampere-Maxwell law tells that closed integral B dot dl over C quantity is proportional to the enclosed current and rate of change of electric flux through any surface bounded by path C. Here in this circuit, current I flows as a battery charges the capacitor. This current produces a magnetic field around the wire, and the circulation of that field is given by Ampere's law. That means line integral B dot dl is equal to mu naught I. Here mu naught I is the conduction current flowing through the wire. According to the Ampere's law, the enclosed current includes all current that penetrates any surface for which path L is a boundary. The product of permittivity and the change of electric flux through a surface is called as displacement current, even though no charge actually flows across the surface. Therefore, the displacement current is defined as by the relation ID is equal to surface integral del d by del t dot ds. And this equation we have already discussed in the electrostatics. And this can be also written as epsilon naught d by dt surface integral E dot ds. And this ID shows that rate of change of electric field will produce the current, and that current is known as displacement current. Thus the Ampere's Maxwell law can be written as closed integral over contour C B dot dl is equal to mu naught in bracket IENC plus epsilon naught d by dt surface integral E dot n cap dA. This is the fourth equation of Maxwell in the integral form. Moreover, Maxwell's provided a hypothesis that the total current flowing through any surface consists in general of a conduction current and a displacement current. Here, mu naught I enclosed is conduction current and epsilon naught d by dt surface integral E dot n cap dA is displacement current. Like the electric field in Gauss law, the magnetic field in Ampere's Maxwell law is hidden within an integral and coupled to the another vector quantity by the dot product. The differential form of the Ampere's Maxwell equation is written as del cross B is equal to mu naught J plus epsilon naught del E by del T. The left side of this equation is a mathematical description of the curl of magnetic field, and the two terms on the right hand side represents the conduction current density, that is J, and the time rate of change of the electric field, that is basically displacement current. And the main idea of the differential form of the Ampere's Maxwell equation is a circulating magnetic field is produced by an electric current and by an electric field that changes with the time. So here expanded view of the differential form is written, in which del is the operator and provided the curl with B. So cross product turns the del operator into curl, and B is the magnetic field in Tesla and it is vector quantity, so therefore it is represented by arrowhead. Mu naught is the free space permeability and J is the conduction current density and it is a vector quantity, whereas epsilon naught is the free space permittivity, and the term del E by del T is rate of change of electric field with the time. So here with the figure you can see when the electric field are changing with the times, the circulating magnetic field is induced across the lines. So this was the prediction done by the Maxwell. So what extra term is added by the Maxwell, that is the displacement current, and this was the one of the main hypotheses given by the Maxwell. Therefore Ampere's law is modified and that equation is known as Maxwell Fourth Equation. Hence all the magnetic fields, whether produced by electrical currents or by changing electric fields, circulate back upon themselves and form a continuous loops. It is important that just because magnetic fields circulate, one should not conclude that curl is non-zero everywhere in the field. A common misconception is that the curl of a vector field is non-zero everywhere the field appears to curl. Both integral and differential form of the Ampere's Maxwell equation are used as per the requirement of the problem solving. So this is about the Maxwell fourth equation. So far we have discussed all four Maxwell equations for the time varying condition, and in the upcoming videos we will discuss all fourth Maxwell equation for the various conditions such as free space, static field condition, time varying condition and time harmonic condition. So stay tuned with us and keep watching my video to understand about the electromagnetic field theory. So thank you for watching this video.